All right, welcome back, Precalcsters. In this video, I am going to be just talking through our key that we're working through on this, and hopefully the volume levels are okay. It seems like it's being kind of quiet, but oh, there it goes. Sorry about that. But we'll go ahead and figure that out. So for this, please make sure that if you are watching this at home, on the road, whatever the case is, if there's places where you're unsure of, please make a note so you can ask a question when we come back. This is being posted on the Friday before the test, which is coming up on Tuesday next week. So let's just jump right in. On these first problems, it says, let's use our calculator to evaluate. Now, all I'm really checking for here is one, that you know how to use your calculator, at least in the most basic sense, but two, that we have a way to distinguish what's going on. And this one, the tricky part that I want you to pay really careful attention to, is that there is no degree symbol. And if there's no degree symbol, it means we must be working in radians. So we'll go to our calculator, we'll put in radians, and I'm just going to ask it, the tangent of 1.72, and it's in radians. We should wind up that this value is approximately, and I'm going to use 4 decimal points unless specified otherwise, approximately -6, we'll try that again, -6.6524. And that's all there is to it. Similar problem on Bravo here. We are simply using our calculator. I notice there is a wonderful degree symbol here. So I will take the time to change my calculator into degrees real quick by hitting mode, going down to, highlighting degree, and hitting enter. Okay, once I'm here, I realize that my calculator does not have a cosecant button, which is kind of a bummer. But rather than starting with approximate, I do know that this is exactly 1 over the sine of 31 degrees, since this is how we define cosecant. So in my calculator, I'm going to type in exactly that, 1 over the sine of 31 degrees. And we should see, and I'll double check my mode here now, but we should see, theoretically, that this winds up being approximately, I just can't find, there we go, approximately 1.9416. Now, point-wise, this would have just been worth 2 points. It's either you got these values or you didn't. Cool. For the second one, I'm going to do all of this with the exception of the actual drawing of the graph. I'll hop over to the other program because it's easier to draw for me. But when I look at this function, f of t, all that I notice right off the bat is that we need a bunch of stuff. So period, there's some jump, some other things that we're going to show. So the period of this, remember, we take for cosine and sine, the period is 2 pi, because that's a regular parent period, divided by b, where b is the coefficient on our variable. Now, in this situation, it's ugly and it's hidden, but the number connected to t is 1/2. So when we plug in b equals 1/2, and I'm using this, a cosine of bx minus c, when I'm referring to these things. So when I plug in b, I see that t over 2 is the same thing as 1/2 t, which is exactly what I'm going to use here. So playing around with this, let's see, we get 2 pi over 1/2, which winds up being 4 pi, because I just multiplied by the reciprocal. So the period's 4 pi. Now, I always use the jump next, and for this particular function, all we do, and any function for that matter, is we take whatever our period we found is, and we multiply it by 1/4. Or, if you'd rather, we can just think about it as dividing by 4. Whichever way we take, we get that the jump on our table winds up being pi. So, super easy to do that. The starting point of our table that we're about to make, we're going to use the fact that I know that normally the parent function begins when I set my argument, bx minus c, equal to 0, because the first natural place you will plug in is 0 radians, and it's logical. Now, I have x here instead of t. Nothing changes except the variable. So let's just put our argument here, which is the thing that we're taking the cosine of, and we see that it's t over 2 plus pi must be equal to 0. And I will subtract a pi and multiply by 2 and see that, hey, the first place on our table is going to be 2 pi. Negative 2 pi, I'm sorry. Now, the only other thing you might write down here would be the amplitude. And I don't typically write it down We talked about it, and we've done these where we didn't necessarily write it, but I do notice that the amplitude is 2. So if we're making our table, and I will do that table up here a little bit more, we have a t value, and then 2 times the cosine of t halves plus pi, and then the f of t value. So going through these, remember there is always a trick that we can use to make these go a little bit quicker. And the trick that I'm using is, if you check your notes, you'll see these, but I know that the parent cosine looks like this. And I'm using this because I know that it starts up high and it goes down 1 amplitude and then down an amplitude and then up an amplitude and up an amplitude. So to use this to our advantage, let's just start. We'll plug in negative 2 pi and we'll ensure that this works out. If I plug in negative 2 pi, and I will check this very first value and I'll check it like really formally to make sure that we get it right. Let's see, if I plug in 2 pi into this, we are going to get 2 times the cosine of, and I'm going to plug negative 2 pi in for t, and that would be negative 2 pi over 2, which is just negative pi plus pi, because negative 2 pi over 2. Okay, looking at this, I see that my argument is 0. So this is 2 times the cosine of 0, and the cosine of 0 radians is 1. So this whole piece winds up being 1, and there's still a 2 that we're multiplying it by, so I see it's up 2. Now from here, I'm not going to think anymore about this other than the fact that it generalizes and it's nice. So I'll separate it here, and I know that I'm going to jump by pi. So if I go pi forward from here, I'm at negative pi. And based on what I know cosine does, it goes down an amplitude, and an amplitude on this one is 2, so it goes down 2, so it's at 0. Take another step, and it goes down another amplitude. We're at negative 2. And then I'm going to have to separate this just so it looks nicer. And let's see, we go up one more, and we go up an amplitude. And I don't know why I didn't write this one. 0 there. Weird. Up an amplitude back to 0, and finally we end up at 2 pi, and we're at 2. Now, for graphing this, and I lied, I will try to do it here. I just can't draw straight lines, so take that, keep that in mind. If I were to graph this on this thing, and I'm about to, I just can't find my mouse. There we go. If we're graphing it here, I'm going to try to show 2 periods of this. So I'll try my best to go down here, and there it is. And it's not perfectly straight, but that's okay. Here's another one. And here's the weird part. Each of my ticks is going to be pi. So I'm just going to choose a convenient one. I want to show 2 periods typically. So for no particular reason, I'm going to say there's pi. And that's 3 ticks. So I'm just going to make my scale here. There's 2 pi, 3 pi, 4 pi. And then here's negative pi, and negative 2 pi, and negative 3 pi, and negative 4 pi. And I have way more than nope, I started jumping by 2s. So disregard that last little spot. And here's my issue with using this program. Yep, knew it was going to happen. All right, so we'll switch to black because that's the one that I selected. And let's see if we can't get this. And we'll do the same thing. 3 ticks was pi. And then here's 1, 2, 3, 1, 2, 3, and then 1, 2, 3. And I'm just marking these off, and sorry, it's just easier for me to do it without pausing it. So I got several points on this here, and they're all looking good to me. And let's just graph it. I start at negative 2 pi, so it's right here, and it starts at 2. So let's say that there's 1, and here's 2 all the way up here, 3 more away. Now, all that we have to do with these, and it's the same way every time, as long as we get this pattern, is I'm just going to start putting them. Negative 2 pi goes at 2. Then it goes down an amplitude, and I need to see 1, 2, 3, 1, 2, 3, and then up an amplitude, and up an amplitude. So I have these points, and they're part of my cosine wave. Now, we're going to resist the urge to make this a sharp turn, and we'll just say, look at this, it's a wave. And it's a wave. And right now we have 1 period of this cosine function. Now, if we need another period, because I have this scale out, and I'm just going to switch color so that it's clear where the second period is, I'm just going to go from here, I'm going to go down an amplitude, and down an amplitude, and we're doing the same thing. and I get another half period of cosine showing up here in green. And if I do the same thing on the other side and I just keep that pattern going, I see that I get another half amplitude right here. And I have 2 full periods of cosine now. So every problem is the same. Period, jump, the starting point, with the exception of we have to be careful if it's tangent or cotangent, the period starts at pi instead of 2 pi. So all fine and dandy here, I hope. For this, I would give you, I think, 5 points for this problem. A point for the period, a point for the jump, a point for the start, a point for the table, and a point for the actual graph. So there'd be 5 total points on this problem. And we'll say there's our 5. Okay. For this, I have secant theta is 13 over 5, and I know that sine is positive. So I'm going to do a little bit of thinking over here. If I know, and I'm going to make that a little bit thicker just so it's easier to see, if I know that the sine of theta is positive, then that means I'm in one of 2 places. I'm in quadrant 1 or quadrant 2, something above the x-axis. Okay, so I'm in quadrant 1 or 2. If secant theta is positive, well, then this immediately implies that secant, which comes from sine, it's the reciprocal, 1 over sine. But if secant is positive, then sine theta is positive, and there's something goofy going on here. Interesting. No, cosine is positive. What am I talking about? Secant and cosine. I'm terribly sorry about that, guys. Don't know why I had a brain hiccup there. So we'll say get rid of that one. If secant is positive and secant is 1 over cosine, then cosine is positive. And now that we know cosine is positive, it means quadrant 1 or 4. Quadrant 1 or quadrant 4. And my stuff doesn't track here as well, so that's why it's coming out uglier. Which means I now know that because the only overlap between these 2 possibilities is at quadrant 1, we're in quadrant 1. So we're bouncing around several different trig definitions here. If I know that secant is what we're looking at, I typically think of cosine first. And I'm going to write them both. Cosine I know is x over r, which means that secant is r over x. And what that gives me is that right now I know that r is 13. That was given up here. I know that x is 5. That was also given in the original little spot. And then through Pythagorean theorem, or the fact that Pythagorean triples exist, either way, we can obtain y equals 12. And as soon as we have all 3 values, these are a piece of cake. Sine is defined to be, for us, y over r. So I'm just going to look. Y is 12, r is 13, and we're done. Which means the cosecant, its reciprocal, is just 13 over 12. Done. Cosine, we can plug in x over r, and we're going to get 5/13. And when we take its reciprocal, which is secant, we get 13/5. Now, I did not just blindly copy what was up here. Instead, I actually did the reciprocal, and then I checked, did it match up? And it's a good little check to see that, yeah, things are feeling okay. Tangent is defined as sine over cosine, or y over x. So it looks like it should be 12 for y and 5 for x. And the cotangent is simply the reciprocal here at 5/12. So this problem would be worth 4 points. Each of these would be worth a half a point, which would get us to our 3 total points. Your other point would come from the fact that you are using x and y and r in some fashion to get these definitions. Cool. All right. So page 1, it looks like then it should have been out of 2 and 5 is 7 and 4 is 11 total points, theoretically. Now, it might be a little bit different because I worked the key the other day and I'm doing it again here just for your guys' sake. But here we go. Now, we did not do problems like these in class. And that's okay because we're going to make sense of this. If I were to write this out, and one, I'm going to use the other notation because I think it's a little bit nicer. But I'm taking the cosine of the arc sine, and I'm going to use red for this argument, even though it should be green. The arc sine of root 3 over 2. Now, it's intimidating at first, but don't panic. This value is not near as bad as it looks. All that this is saying is on the right half of the unit circle, because we restricted from negative pi halves to pi halves, on the right half of my unit circle, is there an angle where the sine is root 3 over 2? And if you check a unit circle with me, you'll agree, I hope, that the arc sine of root 3 over 2 tells me that the theta that we're after is pi thirds. That's the only place on the right half of the circle where sine is root 3 over 2. So all I've done is I've cleaned up the arc sine, the inside piece, if you will, of my composition. And since we've done that, we'll now take care of the outside piece. And we're just asking the cosine of pi thirds. So again, we just find the unit circle. And if you go to pi thirds, which I know that I'm not going to show you a unit circle right here, but pi thirds is like up here. It's the big point, not root 2 over 2. Then this is going to be 1/2. And we're done. On 4, it is an even easier problem than this, which is pretty awesome. And I'm going to write it rather than arc cos. I'm going to use the notation that we use. So I'll use the inverse cosine of the cosine of pi thirds. Now, we could do the same thing. We could find the cosine of pi thirds and then say, what's the arc cosine of this? Or, and this is really what we will do, or we could recognize that a cosine is undone by its inverse. And if we use that logic, it turns out we get the exact same answer. It's going to be pi thirds again, and we're done. It's easy, and it's awesome. If you don't like this, I will show the alternative. Cosine of pi thirds is 1/2. And then we would ask, whoa, cosine of pi. No, what am I doing? Let me back up. I'm sorry. I'm not sure what that was all about. If I do the cosine of pi thirds is 1/2, then we would start with the arc cosine of 1/2. And now the question would simply change to where on the top half of my unit circle, because that's where we restrict arc cosine to, where on the top half of the unit circle is the cosine value exactly 1/2, and you would verify once again that it's at pi thirds. It's the only place that it happens. Okay, number 5. I'm going to talk out my drawing here as we go, and let's just see what we have. A boat leaves a dock. So here we go. Here's a dock, and my lines aren't going to be straight, just a heads up. And we go due west, which is going to be left if we had a compass rose here, and I go 20 knots per hour for 60 minutes, which means over this time I have gone 20 nautical miles. Okay. I then change to a bearing of 28 degrees west of south. So I'm going to do this one really light, and I think I actually just changed the wrong thing. I'm going to use a really light gray color that's just barely visible here to set up a compass rose here. And it's a lot more visible than I was thinking it would be, so that's okay. So here is north-south and east-west. And I'm only doing this so that when I go to set up my next bearing, like when I actually represent that bearing on here, we're going to get a nicer way to deal with it. So I'll go back here, and I should have just put this on the other program. Terribly sorry, guys. So here's my northeast, south, and west. I just put at the end of that 20 nautical mile part. So we go 28 degrees west of south is what it's alleging. So if we're here, and I go from south, west is to the left from this direction. So I'm just going to eyeball here, and that's way too big. I'll make this finer, and I'll keep that for now. But let me look here, color, and the thickness. What we've just found is that this angle is my 28 degrees. Now, I'm fine with that. I also know that that is going to be a 90-degree angle. So we can write 28 degrees here. The alternative would be the big angle is 108. And I'll keep that in mind for now. Okay. Anyway, we are staying the same speed, 20 knots, for 3/4 of an hour, which means we're going to go for this part. I'm going to put this here, 15 nautical miles. Now, we want to head back to the dock. So we want to know how far and at what angle should we go. Now, what that is represented by on this is this lovely dashed line. And I'm just going to call this D for now. Okay. With trig stuff, remember at this point of our course, all the trig stuff that we do is with right triangles. And unfortunately, right this second, I do not have a wonderful right triangle up here. What I do know is all sorts of stuff. Now, the cool thing I think about these problems is that it doesn't really change a whole lot right now. We'll get some more fun versions, but if I were to extend this side out, and I'm going to do it with a different color. If I were to extend this side out, it hasn't changed anything about my original drawing. If I were to extend after that this side straight down, it still doesn't change anything about my original drawing. Nothing has been moved or changed or anything like that. I'm going to just make sure I have this and get that little extra erased off. But we have this new little section of a triangle that we can use. And to do this, it looks like I now have that lovely right angle. So for the current time being, I'm going to call this X and I'm going to call this Y. And I'm going to take this blue triangle out just to draw it a little bit nicer, so we can see the other pieces. So here's that same triangle where it's X, it's Y, it's 90 degrees, and I'm just going to write the other pieces here. This distance, the hypotenuse of this from our other picture was 15 nautical miles. Now, the other part of it that I'm using, the little piece that disappeared, is this big angle from our picture, which is this big angle in this picture, is 108. Now, because these two are a linear pair and they form a straight line, I then know that this is 72 degrees right here. And I have the hypotenuse and an angle. I'm going to start cooking with these things. So let's see. If I were to take the sine of 72 degrees, that would be equal on this triangle to the opposite side, which is y, over the hypotenuse here. Now, I'm going to do some calculation, and I'm just going to multiply both sides by 15, and I'll say that y is exactly equal to 15 times the sine of 72 degrees. But on my end, if I just do the sine of 72 degrees, and let me make sure I'm in degrees here, mode, and I am. The sine of 72 degrees is 0.95, bunch of numbers. I'm just going to use my calculator to multiply it by 15, and I'll say that, okay, y is approximately, and I'm going to put it back on the original, 14.2658 nautical miles. Okay, using a very similar approach and cosine instead, we'll say that the cosine of 72 degrees is equal to x instead over 15. And from this, same thing. Multiply 15 by both sides, and I will have that x is exactly equal to 15 times the cosine of 72. Or on my calculator, 15 cosine of 72 will tell me that this up here, this x value, was simply 4.6353. Okay. So one more little taking a triangle apart and putting it back together. I'm going to do the same thing here, but we're going to use a nicer value. So what I mean by that is on this new big triangle, I said nicer value. That was a weird way to word it. Here's what I know for sure, and this is just a smaller version. The entire top is 24.6353 because I just added those pieces together. 6353. And I'm going to make this less bold because it's driving me crazy. The vertical side over here, we've already found there's nothing to add it to. It's 14.2658. And with a little bit of Pythagorean theorem, I know that if I take 24.6 squared, so I'll just do this on my calculator, and I'm not rounding anything on my calculator, just so you know. I'm using not 24.6353. In my calculator, it says 24.635259492. I wrote the rounded version here, but I'm going to use the big version of my calculator. So I will square that number. So that thing squared plus 14 point, and again, I'm not just going to use those 4 decimals when I'm doing it. I'm going to let my calculator actually do all this big stuff and carry it through, but I'll do the other side squared. And I get a disgusting number. And just so you can have a check, if you were checking with your calculator, when I do a squared plus b squared, I get 810.4102. Okay, I will take the square root of that to get d, and it looks like it's approximately 28.4677. And that would be nautical miles. Now, we have our answer. almost all of it. When we're talking our bearing, all we need is this angle right here. And I know it doesn't show up on this one. Oh, it does show up on this one too. It's this angle right here. And the cool thing is that I know all three sides of this triangle now. So if I have all three sides of this, it doesn't matter which function I use. I'm going to use opposite and adjacent. So I'll use arctangent. And we'll say theta is equal to the arctangent of opposite over adjacent. So we're going from this angle here. Opposite is 24.6353 over the adjacent is my 14.2658. And I'm just going to straight up type this into my calculator. The arctangent of, and I'll even use those decimals this time so our numbers will match. 6353, 14.2658. I get 59.9257. 59.9257 degrees. So the cool thing is that because the way we've drawn this is already going north, or this, if you'd rather look here, it's already running north to south, and I just fall to the east, and we found that angle. So here's the caveman version of this. We go 28.467, 4677 nautical miles at north. We start at and we turn 59.9257 degrees to the east because we fell to the right to return to the dock. Okay, so for this problem, I think, and again, I may be a little bit different, but I think I see 4 points on this. 1 point is, did you draw this? 1 point for, did you find a way to make some right triangle stuff? So I'm going to call that extend is what we did for that. Did you find X and Y? And I guess it's going to be worth more than 4 points. Did you find D? And last one, did you give me an answer with context? Okay. So it looks like we're nearing the end of this here. And right about 30 minutes is where we'll end. So we're given a circle, and I'm given the circumference and an arc length, and I want to find the angle that got us that arc length. So let's think this out. I know that the circumference is 2 pi r for any circle, and furthermore, I know that that's equal to 10 pi. Okay, so all that is just given here. Now, what I'm thinking is I need a way to relate this stuff. So when I'm looking at this, I get 2 pi r equals 10 pi. And if I set these equal to each other, I'll divide both sides by 2 pi. I think I conclude that the radius is 5. Now, we have that. And what other little pieces we have when we're thinking about radians in this thing is we have 2 more symbols that we use. I have a radius, I have an angle theta, and this is what we're trying to find. And I have an arc length that we write as S. Now, my arc length is 25 pi over 4. So I'm just going to put these here. Okay, and all we're trying to find is theta. Now, the cool part about this is if you look at the practice test, or this is the practice test, I'm sorry. If you look back at the quiz or in the early sections, when we first defined radians, we had this show up. S equals R times theta. And this works perfectly. We have S, we have R, we need to find theta. So 1 radian is very specifically, or was very specifically defined as S over R when they're the same. But I can still get theta as S over R. We're just not going to get 1 radian. So all we have to do here, once we have this rearranged, and I'll work downward instead, is just plug in what we know. 25 pi over 4. And then we would divide this by the radius of 5. But what I'm going to do is, instead of writing big divide by 5, I know that's the same as dividing or multiplying by 1/5. And it's easier to simplify. And it looks like we get an angle of 5 pi fourths. And we're done. There's no unit needed. We're in radians. If you gave me degrees, gross, but I'll take it. It should be 200 25 degrees. Okay, that's our angle. S equals R theta is our relationship, and we can get it. Okay, last little ones. I'm hopeful that when you do this, you actually do the work because I'd want you to show the work. If we have something in degrees, we need a clever choice of 1 to multiply by. And we're going to do a half circle over a half circle because it's something over itself. Now, the way we write that half circle is our choice. In radians, it's pi. In degrees, it's 180. I notice my degrees fall out. 45 over 180 simplifies to 1/4. So I have pi fourths. And you can confirm this on the unit circle without a whole lot of issue. On this one, the number is going to be uglier and I'm going to use a calculator, but I'm in radians and I want to wind up in degrees. There's no equation to really solve. I'm just going to multiply by 1 so it changes the way it looks, but not what's really there. So if I'm in radians and I want degrees, it means I need to have degrees up top. So here we are. I see that those divide out. And legitimately, if you say it's exactly equal to 13 times 180 over 7 degrees, I'm okay with it. Now, if you have a calculator handy, which I imagine you do because the last problem required one, if you do this calculation, we wind up getting approximately 334.2857 degrees. And each of these, I'll tell you, is worth 2 because I want to see, are you actually doing the conversion rather than just blindly checking the unit circle? And did you get the right answer? So 31 minutes, super explained. Real strong fingers crossed that I don't have any mistakes with this. Please, if there's any part of this that you're not quite sure about or not comfortable with, don't hesitate to shoot me an email and say, Holloway, I didn't understand what you were talking about on this problem. I'm happy to address it. And it'll probably be addressed on Monday, realistically, while you guys are sitting at home and I'm in service. But I'll see you cool cats on Tuesday, ready for the test. And enjoy your weekend. Study it up. Don't forget your trick cheat sheets with tangents if you put them on there. All right. Later, Raiders.